Let's discuss the notions of resistance and Ohm's law. So I have here a 10 gauge copper wire. Gauge means the diameter. The smaller the gauge number, the heavier the wire is and the bigger the diameter. So for example, a 30 gauge wire would be very thin and a 0 gauge wire would be really thick. And there's also wires thicker than that, like the 00 and the 000. They'll be really thick cables for transmitting a lot of voltage. So let's just take a look at this 10 gauge wire. If you go microscopically and look at it inside, it's made up of copper atoms, which are arranged in a nice lattice called the body-centered cubic lattice, or BCC. Well, there are some valence electrons left over in all this, and those valence electrons are ready to go wherever adventure takes them. Adventure comes in the form of an electric field applied between the two ends of the wire, usually by using a battery or something. Now, when you have a potential difference, those valence electrons are easily convinced to leave their parent lattice structure and go for the ride in search of fame and glory. So they're just going to start traveling. Now, when you have an electric field, you have an electric force. F equals ma means they're going to accelerate, but not for long. As soon as they start accelerating, they're going to collide with some other atoms and they're going to stop. Then the electric field will act on them again, they'll collide and they'll stop. This entire process of stop-start will cause these valence electrons not to accelerate at all, but move with what's called a drift speed or the drift velocity. This drift velocity is actually very small. So when you turn on your light switch, the drift velocity is only a few millimeters per second. Then how come the light comes on almost immediately? Well, that's because it's not the drift velocity of the electrons that communicates the fact that the current flows through the wire, but rather the electromagnetic wave that flows through the wire that travels at the speed of light. So they're two completely different things. Now, what I will be doing in this video is to derive what's called Ohm's law from the wire point of view. First of all, let's look at what Ohm's law is for the physics. So Ohm's law is a statement that the electric field within a conductor and the current density J are related. Now, what is current density? First of all, to answer that, I have to talk about current. What is current? Current is defined as charge flow per unit time, or in the calculus sense, it's dq by dt. Or in other words, the total charge that flows through the circuit at any given time is the integral of I dt from some time 0 to some time t. So that's the concept of current. Current is measured in units of coulombs per second because charge is measured in coulomb and time is measured in seconds. That's got a special unit, and that's called an ampere, denoted by the symbol A, named after the great scientist Ampere. That's the unit of current. Current density is just the concept of current divided by the unit cross-sectional area. It's a vector in the sense that the direction of the vector is same as the direction of the charges that are moving. So I'll call that direction n hat. Normally in a wire, that direction is the same as the length of the wire because the charges are going to be moving along the length of the wire. So Ohm's law is a statement that E and J are related. How are they related? Well, Ohm wrote the following relationship: J equals sigma times E. And this is the statement known as Ohm's law. It means that the two are linearly related. If you double the electric field, you double the current density. That means if you increase the voltage across the wire by 2 times, you're going to convince twice as many valence electrons to leave their parent atoms. So that's the statement known as Ohm's law. The sigma factor here is called the conductivity. This has nothing to do with the sigma that you have studied so far, which is the charge density on a surface, namely coulombs per square meter. This is the conductivity. So sometimes I like to write sigma con just to make sure that you don't get confused with earlier uses of the same term, sigma. I'll talk more about the units of conductivity later, but this is Ohm's law. I would like now to talk about Ohm's law as applied to wires. Most wires, such as the one I showed you, commercial wires, have a constant cross-sectional area, in this case circular. It does not have to be circular, you just have to demand that the cross-section does not change over the length of the wire. So suppose I have a nice commercial sample of wire, one side of which I connect to the positive side of a battery and the other side of which I connect to the ground or the earth. Now what's going to happen here, the perpendicular cross-sectional area is just that. So as a matter of fact, the current density is related to the current just by the following relationships. J equals I over A perpendicular. And just to keep things simple, I'm going to call it just A. All right, let's call the length of the conductor L. What would the electric field be across this conductor? Well, because it's a constant electric field from the top to the bottom, the electric field is going to be constant. It's a uniform wire, so the electric field is going to be constant. The electric field is just a change in voltage divided by the change in length, and the change in length is just L. So that's just it's going to be V over L. All right, let's put these two in Ohm's law and see what we get. And I'll remove the vector signs. J is just I times A perpendicular, and that's equal to sigma con times V over L. Okay, let's move everything to the other side. So I'll get V equals A times L over sigma con. I think I made a mistake here. J is equal to I over A, not it's I over A. So this equation has to be modified a little bit. Let me use my magic whiteout to do that. Okay, let's redo this bit. So I over A equals sigma con V over L. Now I'll move all the stuff to the left side. So I'll get I L over A sigma con equals V. Let me rewrite this. This gives me V equals I over, let me write the L first. L over A sigma con times I. Now this is getting more familiar. Those of you who have studied the subject before know that you need to have V equals IR. That is the classic Ohm's law that engineers use. But this doesn't look anything like that unless we define R to be equal to L over A sigma con. Well, let's do that. The resistance of the wire is defined as L over A sigma con. Now the conductivity of a material is not as famous as the resistivity. So resistivity and conductivity share the reciprocal relationship. So this is sometimes written as rho res L over A, where sigma con equals 1 over rho res. Now observe that I have called conductivity reciprocal to be rho res instead of just rho, because I don't want you to confuse rho with an earlier use of rho for volume charge density. So sigma and rho are unfortunate here because we've used them both when we studied Gauss's law. So for that reason I have put decorations on them, these subscripts con and res respectively. So this is called a resistivity, and that's called the conductivity. And written in this way, this is the Ohm's law for wires. And in general, resistors, not everything satisfies Ohm's law. In fact, things that satisfy Ohm's law are called ohmic, and things that don't satisfy Ohm's law are called non-ohmic. For example, if you have a semiconductor diode, that's non-ohmic. Even a light bulb is non-ohmic because as the current flows through the bulb heats up, and the heating of the bulb causes atoms to move faster and cause more resistance to the valence electrons, and so that resistance does depend on temperature and so forth. So it's a complicated process for a bulb. Now for the units, as I promised. The units of resistance are definitely ohms, because we have to honor ohms somehow, and he was the person who did all these investigations. The symbol ohm is denoted by the capital letter omega. Well, if resistance is measured in ohms, that automatically tells us what rho res is measured in. So the units of rho res, remember this is rho res times meters over meters squared. So rho res over meters must be equal to ohms, or rho res must be ohms times meters. So the resistivity is always measured in ohm meter. What about conductivity? Well, because conductivity is the reciprocal of resistivity, you might think that conductivity should be written as 1 over ohm meter. And in fact, electrical engineers for the longest time did that. They also had a sense of humor, so they brought this ohm in the denominator upstairs and made it upside down like a horseshoe, and they called it mho. So it's mho per meter. So for some time, this joke was carried out, and then some less amused people in France said, "No, you can't do these kind of things. The joke's gone too far. We're going to give SI units to sigma con, and sigma con is now going to be called Siemens by the German engineer Siemens, who was responsible for a lot of the motor technology that we have today. There's even a Siemens company that makes motors in Germany and worldwide. So those are the units for conductivity. I think it's Siemens per meter instead of this funnily shaped ohm read backwards. Mho is ohm read backwards. So those are the units, and this famous law, V equals IR, is called Ohm's law. Now there are funny ways to remember Ohm's law. If you look at old army field manuals, you'll find that in these army manuals, they write Ohm's law like this. Why? Because I guess it's possible to forget what Ohm's law is. So VIR, in this way you'll never forget it. V is equal to IR, I equals V over R, R equals V over I. And in some of these army manuals, these are called the 3 laws of Ohm. Well, of course, there's only one Ohm's law, but you can think of each way of writing it as a separate law if you wish. But anyway, I thought that was a funny thing to mention.